Okay, sir. Okay, sir. Earth Day is an annual event on April 22 to demonstrate support for environmental protection. It was first held on April 22, 1970. It now includes a wide range of events coordinated and conducted globally. Respected President ISRS and Director NRSC, Dr. Prakash Chauhan, Director Wadia Institute of Himalayan Geology, Dr. Kalachand Sain, sir, all ISRS Executive Council members, ISRS members, and audience. On behalf of ISRS, I extend a very warm welcome and a very good afternoon to all. As you are all aware that Earth Day is celebrated annually to raise awareness among the masses about the current environmental issues and inspire them to act towards the protection of the environment. The theme for this year's Earth Day is Invest in Our Planet. The theme this year focuses on acting in a bold way, innovating in a broad way, and implementing in an equitable manner. Indian Society of Remote Sensing, a premier professional society, is dedicated towards promotion and dissemination of remote sensing and GIS in India. Every year on Earth Day, ISRS invites a distinguished scientist in the country to deliver a popular talk on this occasion. This year, ISRS has invited a very distinguished scientist and outstanding professor, Dr. Kalachand Sain, Director, Wadia Institute of Himalayan Geology, Dehradun, to deliver a talk on the topic Gas Hydrates, Future Major Potential Energy Resources in India. Though our distinguished speaker needs no introduction, but still it is my proud privilege to read out his brief biodata. Dr. Kalachand Sain did his BSc from Burdwan University, MSc in 1988 from ISM Dhanbad. He has a PhD from Osmania University and a postdoctoral fellow at Cambridge University, UK, and Rice University, USA. Dr. Kalachand Sain is currently Director, Wadia Institute of Himalayan Geology, Dehradun. He was formerly head SciR, NGRI, Hyderabad, and an outstanding professor at the Academy of Scientific and Innovative Research, Ghaziabad. Dr. Sain specializes and has research interest in diverse areas such as inversion modeling, processing and interpretation of geophysical data, seismic travel time, and full waveform tomography, AI and ML for rock physics modeling, attribute characterization, to name a few. Now I would request Dr. Prakash Chauhan, President ISRS, to welcome the distinguished guest.
Thank you, Dr. Poonam. All the distinguished members of Indian Society of Remote Sensing, and most importantly, the chief guest of the day, Dr. Kalachand Sain, Director of Wadia Institute of Himalayan Geology. Good afternoon to all of you. And on this occasion of Earth Day, which actually was celebrated on April 22nd, as has been told by Poonam, we are, celebrating this today. And we have invited a very eminent speaker to talk about, the potential alternative energy sources, and one such energy source which can be of immense use in future to come is gas hydrates. And Dr. Kalachand Sain is an expert geophysicist who has done extensive work in the field of exploration of gas hydrate resources in Indian context. Now, as all of you are aware, Indian Society of Remote Sensing is a professional society where we have more than 5,000 members which are distributed across this country. And the society is pretty active in terms of organizing large amount of awareness program, especially in the field of remote sensing and and to give platform to the members for having invigorating scientific. We also conduct annually a symposium, at selected place where large amount of gathering is there. And then we also celebrate various, various days which are related to, as far as environment day is concerned, remote sensing day is concerned, and now the Earth Day is also being celebrated. Indian Society of Remote Sensing, as you are all aware, also brings out a monthly journal called the Journal of Indian Society of Remote Sensing, and the journal is doing pretty well. So I also request all the ST members, those who are joining today, to look at our website of Indian Society Journal and definitely contribute towards the growth of our journal. As far as today's event is concerned, I thank Dr. Kalachand Sain immensely that in spite of his very busy schedule, last 3 days he was involved in their annual research advisory committee meeting. Sir, you could take out some time, and we are so grateful to you that you are going to talk to our members today on a very important topic, which definitely matches very well with the theme of this year's Earth Day, that is invest in our planet. And definitely the kind of work which you are going to talk about, especially in terms of exploration of the gas hydrate resource, is a true example that how technological investments, is going to lead a way forward as far as our energy security in this country is concerned. And all of you are aware that, mostly the global economy today is dependent on the hydrocarbon resources, but it has its own limitations. The resources are also finite. And also we have issues related to climate change. So definitely we have to look for the alternate sources of energy for our futuristic needs, and gas hydrates, are going to be the future. So definitely today we will be very, we are very blessed that we are going to hear to your talk, and you are going to tell us about the state of art in this field, as well as Indian efforts and how we can have a roadmap as far as the energy security is concerned. Thank you very much, sir. And once again, I welcome all the members for today's talk. Thank you.
Thank you so much, sir. Now, without wasting more time, I now invite Dr. Kalachand Sain to deliver today's talk. Sir.
Poonam, my slides are visible? My slides are visible, Poonam?
Yes, sir. Now they are visible.
Okay. So it is going little slow, or lag is there. Anyway.
Yes, sir.
Very good afternoon. First of all, I thank President ISRS for invitation and giving me an opportunity to speak on this very important day, Earth Day. Poonam, who is organizing this program, and all the esteemed members of ISRS. Today, I have chosen a completely different topic, what I pursued and still I have been doing on gas hydrates. At NGRI extensively, we did this work. And the gas hydrates are considered future major potential energy resource, not only for our country, but for many countries, particularly in the Asia-Pacific region. So if you look into the scenario, for the economic growth of any country, it is the energy security which drives that. And different forms of energy can contribute towards the security of that country. In our country, whatever energy resources we have, only we can meet to the maximum extent of 30%, and that also mostly are made by oil and gas, natural gas. Already Dr. Prakash Chauhan has mentioned that. And to run our country, we are importing huge amount of oil and gas from outside and spending huge exchequer. So there lies a tremendous responsibility to the geoscientists, to the explorationists, for the exploration of the energy, not only hydrocarbons, but various forms of energy. Altogether, it is a huge deficit. 70% we have to meet either by the conventional oil and gas, or by non-conventional, or by any other renewable energy resources like solar, wind, geothermal, nuclear, hydrogen, or when I say that non-conventional means they can be gas hydrates, they can be shale gas, coal-bed methane, or various other forms of energy. I will touch upon today one of the important component of the country's energy security that can be made by which that particular product is gas hydrates. Many of you do not know what are gas hydrates, where do they occur, how can we identify them or explore them, what are the resource potential, whether the resource potential can meet our overwhelming energy requirement. All these questions are there in our mind. So I'll try to make you one by one all these questions related to their answers. All of us know that during the last few decades, even if entire world heavily depends on the hydrocarbon energy, we are talking about green energy, we are talking about impact of the global warming because of this carbon footprint. We don't need any energy that will produce any carbon dioxide. So all sort of discussions are taking place at various forums. But till date, we couldn't make any breakthrough either in the solar energy, wind energy, nuclear energy, or any energy. Till date, 80% of the world's energy requirement is made by fossil fuels. Of course, coal produces a lot of carbon dioxide, then oil produces, and then gas produces little less. So this is the order of carbon dioxide production, starting from coal, oil, then natural gas. So we are heavily dependent on the fossil fuels unless there is a breakthrough in other domain of renewable energy resources or other energy resources. And it has been envisaged that the fossil fuel reserve is also finite. Maybe after 2060, 2050, we'll be having different set of scenario. So we have to prepare ourselves that we have to explore some of the non-conventional energy resources. One of them is gas hydrate. And if you produce gas from the gas hydrates, again, its constituent is methane. So if you burn methane for production of energy, one carbon is there. So it produces less carbon dioxide compared to other gas like ethane, propane, much less than the oil and much less than the coal. So there lies the importance of exploring the gas hydrates. It is generally considered as a clean hydrocarbon energy. We are talking about the green energy, but gas hydrate is considered as the clean hydrocarbon energy because of main constituent is methane, CH4. We are also looking into the exploration of the hydrocarbons into the deep water, into the thrust fold belt region in like Himalaya. We have been pursuing at WIHG Institute. Some of the work we have done in Assam, Arakan, Upper Assam, as well as in that Himachal Pradesh, where we have Jwalamukhi. So some sort of research we have been doing in the thrust fold belt. Some more research we have been doing into the deep water region. Some work we have been doing into the coal bed methane, shale gas, shale oil. All have some sort of limitation as well as some sort of advantages. Gas hydrates has stolen a limelight because of certain advantages of that. One of the main advantage of gas hydrate is that I told that it produces least carbon dioxide of all hydrocarbon energy resources. So that's why it is called clean hydrocarbon energy, number one. Number two advantage, the existence of the gas hydrate into the Indian offshore is huge. So huge that if we produce only 10% from the gas hydrate reserve present into the Indian offshore within the exclusive economic zone, we'll be able to meet our energy requirement for several decades. And if we can exploit the whole amount of gas hydrate, maybe 1,000 years. So whatever energy deficit we have, whatever energy requirement we'll be having in future, because this estimate today, whatever we have been doing, after 50 years, 100 years, that estimate will be varying. The requirement will be much more. So at the present rate of consumption, we estimate that whatever reserve is present into the Indian offshore, if 10% we exploit, we can meet our energy requirement for several decades. So there lies the second importance. Third importance, in the beginning there were a barrier for the production of gas from the gas hydrate reservoir, but during the last few decades, there have been some sort of test production in America, in China, in Japan, in Canada, and they have demonstrated that gas from the gas hydrate reservoir can be produced economically and environmentally safe way to meet our requirements. So we are talking about gas hydrates, but what are gas hydrates? Many of you do not know. To give a simple definition of the gas hydrate, it is nothing but the pointer, I'll find out. Yeah. It is nothing but a crystalline form of methane and water. 99% is methane and remaining water, formed at very high pressure and low temperature, and looks like ice. You can see over here. So basically, gas hydrate is nothing but ice-like crystalline substances consisting of low molecular weight hydrocarbon like methane, 99.9% is methane, and remaining water, that are formed at high pressure. When I say high pressure, how much pressure? It more than 3 megapascal or 4 megapascal pressure. And low temperature, when I say low temperature, it will be less than 10-15 degrees Celsius, depending on environment. Where they can be found? They can be found out into outer continental margins. They can be found in the permafrost region, or like into the polar regions, we can find out gas hydrates. When you talk about Indian context, they are available only into the outer continental margin, into the deep water, where water column exceeds more than 350 meters. When I say exceeds 350 meters, because 100 meter water column can exert a pressure of 1 megapascal. So you want to have more than 3 megapascal, 3.5 megapascal pressure, then we should have water depth more than 300 meters, like that. So the definition is fine. We can understand where do they occur. We also see what are the constituents. Then happy news or good news, whatever I told in the beginning, that 4 countries have produced gas from the gas hydrate reservoir, but in the test mode. You can see that in 2002, 7, 7, 8, from the Malik site in Canada, based on thermal depressurization method, they produce gas of the order of 515 meter cube, 830 meter cube, 13,000 meter cube. And you can see with the progress of advancement of technology, they produce more and more gas, but they produce only for 5 days, 12.5 days, and 6 days. Similar thing in America, they produce gas from the gas hydrate reservoir in Ignik, Sikumi. They also produce around 6 weeks and that was of the order of 24,000 meter cube of gas. Nankai Trap in Japan, based on depressurization method, they produce gas hydrate for 6 days, 120,000 meter cube. And Senu Sea in the South China Sea, they produce 7 days, 19 hours, 120,000 meter cube of gas, then they stopped. So from this experiment, we can understand that production of gas from the gas hydrate reservoir is possible. But then a question arises in your mind, why did they produce only for 5 days, 6 days, then they stop? Because so far the technique for the production of the gas from the gas hydrate reservoir is not complete, because most of the gas hydrate reservoir was sand reservoir. After 5 days, 6 days production of gas from the gas hydrate reservoir, the sands themselves start getting produced. So we need to develop or further upgrade the technique for the sand mitigation, and for that a lot of efforts are on, and all these very important countries, you can see Canada, America, Japan, China, they are in the leading front for the production of the gas hydrate, and we envisage that in time, maybe after few decades, they will be come out with a complete production technology by which we will not be able to face any sort of problem or sand production or anything else. They will be able to produce gas from the gas hydrate reservoir continuously for the economically as well as for the domestic purposes. I told that gas hydrates are stable at high pressure and low temperature, but problem comes that since they are stable at high pressure and low temperature, they occur into the submarine environment, they occur into the permafrost environment. The moment you start producing from that environment and bring to the surface, at the surface temperature and pressure, they are no more stable. They get dissociated into gas, and that gas simply escapes. So you cannot excavate or you cannot produce just like we produce minerals, any sort of gold, other minerals or oil, gas. Even at what in situ condition they exist, even if you bring out, they will exist into the same state. But in the case of gas hydrate, that's why this production is difficult. Unless you maintain that same high pressure and temperature, low temperature, you will not be able to have that crystalline state of gas hydrates. It will start dissociating and it will escape, and it will escape haphazardly to the atmosphere. Then main constituent methane again is a very dangerous that greenhouse gas, more than 25 to 40 times potent as a greenhouse gas than carbon dioxide. So you can imagine, if you do not produce the gas, methane gas from the gas hydrate reservoir in a controlled way, then you will be adding a lot of methane to the atmosphere, and methane addition to the atmosphere, you will be causing tremendous global warming, because it is much more greenhouse efficient than carbon dioxide, 25 to 40 times. We have to be very, very careful. So in the beginning, people thought that it simply can be produced, but now we can understand it has to be produced such a way that it would not vitiate the environment. And when we talk about global warming, we have talked that addition of the methane to the atmosphere, but in the environment, in the marine environment, wherever they exist, if simply gets dissociated, then they may cause slow failure, the disaster into the marine environment. So a lot of things are there. People are talking about, they have done a lot of research. So we have seen that. Only that hope is coming from this type of experiment. And once we come over or come across all the barriers, the day may take 2 decades or 1 decade time, we'll be able to produce gas from the gas hydrate reservoir. And once we get the technology, you can imagine that how much amount of gas in the form of hydrate is stored into the Indian continental margin is so huge. Again, I am repeatedly telling that amount can meet many centuries of our energy requirement. So from the energy security point of view, we need not think much. So next question will be coming. So we have understood what is gas hydrate. We have also understood where do they occur. We have also understood their potential. That's why we call that major potential energy resource of our country. So much energy resource we have not got in any other resources. But the next question arises, how can we identify them? How can we explore them? Not only to explore them, how can we evaluate that how much amount of gas is stored in the form of hydrate? So there are a lot of geophysical techniques we have also developed. When we say we have developed, when we worked, myself and my students, we have done at NGRI, CSR NGRI, and based on those approaches, based on those seismic techniques, we can identify where are the gas hydrates. We can characterize the gas hydrate reservoirs. We can assess how much amount of gas is present in the form of hydrates. So generally, gas hydrate occur below the sea floor up to few hundred meters. Below further, gas hydrates cannot exist because we have told that gas hydrates occur only at high pressure and low temperature. So as you go down and down, pressure you are getting more and more, that is good. But parallelly, you are getting more and more temperature, and that high temperature doesn't allow hydrate to be stable. It gets dissociated into gas. So from the sea floor up to few hundred meters, wherever gas hydrates are stable, we call gas hydrate stability thickness map, gas hydrate stability zone. And below the stability zone, the gas hydrates are no more stable. If any gas come from below and stay below the gas hydrate stability zone, they will exist in the form of free gas. And gas hydrate is a very, very high velocity compared to the velocity of the host rock. These are all shallow sediments. The velocity of the shallow sediments in the marine environment will be of the order of 1.5678 km per second, but velocity of pure gas hydrate is 3,800 meter or 3.8 km per second. Therefore, their presence into the pore spaces of the marine sediments will enhance the seismic velocity, and the gas hydrate layer, if we do the tomography, we'll be able to know that gas hydrate layer is associated with the high velocity. Even if there is no free gas, if free gas is present, the velocity of the underlying layer will be much lower. Even if velocity, that free gas is not there, simple water exists into the pore spaces of the sediment, the velocity below the gas hydrate stability zone will be low. So therefore, there is a physical contact between the high velocity gas hydrate layer above and low velocity water bearing or gas bearing sediment below. The sediment may be same, top and bottom sediment. It is not the sediment contact. Because of the presence of the gas hydrate, they are creating a high velocity layer and low velocity layer, and that interface is defined as the base of gas hydrate stability zone, along which, if we look into seismic data, it produces a seismic reflector we call bottom simulating reflector. So this is one of the marker for the identification of the gas hydrates. So if gas hydrate is there, they will produce a physical interface between the high velocity gas hydrate bearing sediment and low velocity water or gas bearing sediments. And that interface on the seismic section will appear as a bottom simulating reflector. How do we know this is a bottom simulating reflector associated with the gas hydrate? I will also come back to that. But why do we say bottom simulating reflector? We say bottom simulating reflector because I'll be showing you a couple of examples. Whatever will be the nature of the sea floor, if you look into that particular reflector, this will simply mimic the shape of the sea floor. That's why it is called bottom simulating reflector. You see that the sea floor has been bulged. This also has been bulged over here. This you can see has gone down. This is also going down. So it mimics it doesn't go parallel, but it mimics the shape of the seafloor. That's why this particular reflector, BSR, what we are calling as a marker for the gas hydrate, also mimics the shape of the seafloor. So this important feature of identification of the BSR from the seismic data is important from 3 points of view. One is that if you look into the polarity of this particular reflector with reference to the seafloor, if you go, that water has low velocity. The moment you go to the sediment, it has high velocity. So if you have the positive polarity like that, the moment you process the BSR from high velocity hydrate to low velocity gas, you'll be having negative polarity. So polarity reversal is one of the characteristic property to identify BSR, number one. Second important property, we say that it has to mimic the shape of seafloor. So whatever pattern of seafloor is there, it will mimic to that. Third important thing, we have defined that this is not a lithological boundary. This is a particularly physical interface. So if there is any dipping strata, this physical interface will cross-cuts. The cross-cutting phenomena also will be observed. So 3 important property we have told. 4th important property already told, that from the seismic tomography, if we have high velocity above and low velocity below, because that is another property for the free gas water bearing sediment below and hydrate bearing sediment. From there also we can understand that there is a BSR. 5th important property, I'll come back to that. And from this figure, you can also know that this is the BSR. So in a typical continental margin, you can see as you go down and down towards the interior into the continental rise, then your temperature to the seafloor goes down and water depth increases, and all these phenomena increases the thickness of the gas hydrate stability zone. So this is, you see that this is the base of the gas hydrate stability zone, and it mimics the shape of the seafloor. That's why we call it simulating reflector. This is one of the diagram I am showing to you. I told that in the marine environment, particularly into the slope region, these are all sedimentary strata shown by this, shown by this, shown by this. And if there are some faults, and through the faults, gas can migrate upward, and this is the gas hydrate stability zone, this is the BSR we told. The moment it enters the gas hydrate stability zone, the gas cannot exist no more into the gaseous form. They will form a solid gas hydrate, and they will be deposited over here. And once they deposit, it is a solid, they will reduce the permeability, and once permeability is reduced, they act as a cap rock, and further gas coming from below trapped underneath. So this is the mechanism. That's why we get that high velocity gas hydrate layer above and low velocity free gas layer below. And you can see that BSR form like this because this is an interface between the hydrate and between the hydrate and the gas bearing layer, and this goes like this. So it doesn't matter whether the geological strata are dipping, it will cross cut. So this is cross cut phenomenon. Important is I told. So very important thing, and that is very, very important, that we have said that gas hydrate are stable up to few hundred meters below the seafloor, and the thickness from the seafloor up to that BSR, we have defined gas hydrate stability zone. And in that zone only gas hydrates can occur. Gas hydrates cannot occur into the water. Gas hydrates cannot occur below that, only into that zone. If we look into that physical parameter, I'll go back again, that sea bottom temperature, then water depth, and the geothermal gradient. These 3 parameters control that how much thickness we should have for the gas hydrate stability thickness. So if one area geothermal gradient increases, that means that thickness of the gas hydrate stability zone will be decreasing. If geothermal gradient decreases, then thickness of the gas hydrate stability zone will be more. If seafloor temperature increases, remaining other conditions same, then your gas hydrate stability thickness will be less. If seafloor temperature decreases, then gas hydrate stability thickness will be more. There will be some other additions of chlorine and other salts. Presence of these salts will move the phase duct this side. That also will reduce the thickness of the stability zone. There are so many factors play a role, and if we can understand from the geophysical, geochemical, geological studies, we get all the parameters and we'll be able to know what will be the thickness of the gas hydrate stability in that area. The factor which control the gas hydrate stability thickness are bathymetry, the water column I told, seafloor temperature, then there will be geothermal gradient. Based on that, three important parameters, we have prepared the gas hydrate stability thickness map. This is theoretical map. Why we have prepared this theoretical map? Because the gas hydrate stability thickness says up to what depth gas hydrate can exist below the seafloor. That means where we can expect the BSR. So if we have a seismic line over here and find out a particular reflector based on all those characteristics we have defined as BSR, and then if it coincides with the thickness, then we get ascertained that that is the BSR associated with the gas hydrate. Because it is matching with the gas hydrate stability thickness map, it is also having all those characteristics property of the BSR on the seismic section. To get certainty, to validate, to understand that whatever we have identified BSR, that is really related to hydrates or not, it gets confirmation. So this is very, very important, and this map we have already prepared. These are available into literature. So wherever seismic data exists, and if we process the data, identify a reflector as BSR and find out they are coinciding, we are getting confirmations. If we look into the certain parameters like seafloor temperature, bathymetry, and geothermal gradient we talked about, besides that, we need to understand what is the rate of sedimentation, what is the TOC content, what are the sediment thickness. All these parameters, when we looked into, we have seen that eastern offshore is much more favorable for the formation of the gas hydrate than that into the western offshore. So we have made extensive study into the Mahanadi, Krishna Godavari, even Andaman, Kaveri, and found out that widespread occurrences of the BSR. So this is the first point for the identification of the BSR. Then using the seismic tomography, we can understand what are the velocity configuration. I will show that example. It will be easy to understand. And based on certain formula, area, layer thickness, net gross ratio, porosity, gas hydrate saturation, cage occupancy, we can evaluate some sort of resource potential into the entire continental margin. And we have seen roughly 1900 trillion cubic meter of methane exist in the form of gas hydrates within the Indian exclusive economic zone. And this is more than 1500 times of country's present gas reserve. And if we can exploit only 10%, already I told, it can meet our requirement many, many decades, 7 decades, 8 decades, maybe 100 years. Huge potential. So once we say that we have identified gas hydrates, then gas hydrates should be there within the seafloor to BSR. How much gas hydrates will be present? What are their physical characteristics, chemical characteristics, all these things. If we really want to understand, then we have to characterize the gas hydrate reservoir. This is one of the example I am showing from the Arabian Sea. This is the BSR. This is seafloor. And here gas hydrates will occur. And I told that if there is dipping strata in a environment, then BSR will cut across. You see that BSR has cut across all the dipping strata. So if we look into some of the attributes computed from the seismic data into this region, what we see, there has been amplitude reduction, and the amplitude reduction is defined as blanking. So the blanking is one of the important attributes for the occurrences of the, or for the characterization of the gas hydrates present within the gas hydrate stability zone So that also we have done. Another important characteristic property will be there. We have defined that BSR is an interface between the hydrate above and gas below. If gas is present, then it will be associated with very high reflectivity because of the alternate gas pore strata will cause high reflectivity. And we have seen below the BSR another important attribute, high reflectivity, that shows the presence of the gas. Third important thing, we know since hydrate is a solid crystalline substance, the attenuation property of the solid is much less than the attenuation of the gas or water. So when we computed attenuation property, then we found that within the gas hydrate zone, the attenuation is very low, and attenuation and seismic quality, they are inversely related. That's why we got very high quality factor. Very high quality factor means low attenuation. And if we look into below, then we can see there is a high attenuation or low quality factor. So based on computation of certain attributes, we further characterize the gas hydrate reservoirs. So this is second step. First we have identified, then we have characterized, and step by step we confirm, we get ourselves ascertained, yes, gas hydrates are present over there. So what is remaining now? I will be able to assess how much amount of gas is present in the form of hydrate. Already I explained that gas hydrates are having higher velocity than the sediments, oceanic sediments, in which normally they occur. And if gas hydrates had not been there, we could have expected velocity like this, dashed line. Because of the presence of the gas hydrate and depending on the saturation, the velocity has been increased above the BSR. And because of the presence of the free gas, again depending on the saturation, the amount of decrease, because of the concentration of the hydrate, amount of the hydrate, the amount to increase, all will vary. But main thing, the moment gas hydrates are present, the velocity will be enhanced. Free gas is present, velocity will be dropped. So across the BSR, we can expect high velocity and low velocity. Another important attribute. And once we do that for particular interface, this is the BSR. We see this is the high velocity, this is the low velocity. If you look into the velocity plot, what is this one? Okay. If you look into the velocity plot, you can see blue is low and red is high, and these blue gas-bearing sediments are over and hydrate-bearing sediments are over. By this way, you can delimit that how much sediment content hydrate. Whatever hydrates are there, they will be associated with the high velocity. So in this 2D profile, you know this is the zone of hydrate-bearing sediments and this is the zone of the gas-bearing sediments. Okay, so you have found out that hydrate-bearing zone, gas hydrate-bearing zone, there are thickness variations. Now, for the assessment of the gas present into the hydrate, for the assessment of the gas present in the form of free gas below the BSR, we will be doing rock physics. Rock physics is nothing but a tool by which you can relate the porosity, the rock composition, the saturation of the hydrate or water, everything. So there is a perfect formula. If suppose this rock consisting of 85% sand and 15% clay. So you know my rock consisting of 85% sand and 15% clay. There can be many other simple examples. And you know that rock has 40% porosity. And in the 40% porosity, you know that maybe only 5% are filled with hydrate, remaining 95%. 95% of the 40% porosity. When I say 40% porosity of the rock, that means matrix is 60% and 40% is porous space. And when I say 5% is gas hydrate is present, out of 40% spaces, only 5% is filled with hydrate, remaining are filled with water. So rock physics is a formula that gives the seismic velocity by relating with the rock composition, porosity, as well as saturation of the hydrate, saturation of the gas. So using the rock physics model, this is a simple formula I am telling you, but there will be much more complicated. I'm not going to touch upon to you. just to give you a flavor how we can compute or assess the amount of gas present into the hydrate or amount of gas present in the form of free gas below the BSR using the rock physics model. So this is the rock physics model. What we have done at BSR, by employing the rock physics model, just at the top of the BSR, we have found out the gas hydrate saturation varies between 4% to 15% along the line. And below BSR, the gas saturation varies less than 3.5%. Just to rock physics, whatever I told you. So this way, we can find out the saturation varying along the profile just above the BSR, saturation of gas varying along the profile just below the BSR. But what is happening saturation into the upper part, vertical variation? That also we can do. For that, suppose we have seismic velocity variation based on isotropic, based on anisotropic modeling, we can determine the saturation of the hydrate. Here I am showing one example of gas hydrate present into the fractured clay. Since fractures were present into the sediments, clay sediment, there have been anisotropic behavior. And we have also a log drilling position. In the drilling, we collected some, we also did some logging, as well as we also collected the rock samples. That means the sediment coring also done. And we understood from the drilling and coring into this region, this is one of the seismic section, this is the BSR, this is the locations, this is the seismic velocity, and based on that rock physics modeling, assumption of isotropic, we calculated the saturation of the hydrate like that. Based on anisotropic, we calculated the saturation like this green. And since it occurred into the fracture clay, because of the fracture, the sediment behaved anisotropic, and anisotropic fulfilled, because this is the measurement from the core data, pressure core data. Pressure core data, we got saturation of the hydrate. So pressure core only at selected depth we know, but from this experiment of rock physics and log, we can understand the variation of the saturation vertically. So earlier we saw variation of the hydrate horizontally. Now we are getting saturation of the hydrate vertically. So if you have a combined or maybe effective medium modeling, maybe other sort of modeling, two-dimensional, we will be able to get both variation, horizontal direction and vertical direction. And we have already known how much sediments are having hydrate because of the travel time tomography velocity enhancement. Then in that domain, total amount of hydrate or total amount of gas below the BSR, we can find out using the rock physics model. From the seismic data, we can understand what are the velocity enhancement against the background time, and then using rock physics, that we'll be able to know that velocity increment because of the presence of the hydrate that can be translated for the saturation of the hydrate. So this is simple. So I'm just telling you very simple procedure for the identification of the gas hydrate, for the characterization of the gas hydrate, for the assessment of the gas hydrates. And that's what we have done and given that value. And based on that value only, we are telling that around 10% production will be sufficient to meet our energy requirement for about 100 years or 70, 80 years. So what I showed in the previous slide, that if we have the vertical profile, and for that vertical profile, we have to have the drilling. But drilling is a very costly affair. Everywhere you can't drill. For the validation, presence of the gas hydrate, you can drill. But for that experiment, resource evaluation, we can't drill. So can we assess, can we generate a vertical profile, what we got, without any drilling? To answer to that question, what we have done very sophisticated full waveform inversion. And in the full waveform inversion, the seismic field data is matched with the synthetic data sample by sample. The time, the amplitude, the frequencies, the phases, everything contained into the seismogram is matched. And once you match that, you are able to produce very accurate seismic velocity. I'll give you an example. This is one of the field seismogram, real seismogram has been shown by blue. And we have matched it by full waveform inversion, and the synthetic seismogram has been shown by red. And if we look into the match between the field data and the synthetic data, have been perfectly matched, almost matched. And corresponding to that synthetic seismogram we have generated corresponding to a velocity as a function of depth, and you can see all the finer details. If you do the travel time tomography, the resolution of the travel time tomography is much less than the resolution we obtain from the full waveform inversion. Another example, that synthetic data matched with the observed data, full waveform has been matched, and the finer details. By doing the travel time tomography, we get the velocity as a function of depth that has been shown by dashed line. The moment you do full waveform inversion, you get all the finer details. And it was not evident that 150 meter thin gas layer came out because of the full waveform inversions and perfectly matching with the data. So whatever we saw into the drilling by taking into the log, similarly we are performing full waveform inversion and getting the finer details of the subsurface, and that gives a lot of information to understand or to evaluate the resource of gas hydrate, resource of free gas into that region. Based on that, NGRI itself, we conducted a very big experiment both into the Mahanadi basin as well as KG basin, and these are the lines we are showing, black lines where seismic data were acquired, and all these data have been processed, and based on the characteristics of the BSR, we have identified at few places of the BSR which has been shown by white, but they are not few. They are widespread into this region, they are widespread into this region. So out of the entire seismic data collected along the black lines, both inline and cross line in both basins, Mahanadi and KG, the places where we could identify BSR that have been marked by white, and these are the places where gas hydrates are present. Few examples I am showing over here. I told the BSR name itself shows bottom simulating reflector. So if you look into one of the seismic section in the KG basin, you just look at the sea floor, and the BSR also has mimicked. Whatever nature is there, that's why we call it BSR, bottom simulating reflector. Simply it is dipping, the sea floor is dipping, the BSR also simply it is dipping. And based on several other characteristics, property, whatever we have shown, these have been ascertained, these have been validated. These are the two examples I am showing over there. Some more examples I am showing into the KG basin. This is also one BSR. There is also one BSR. Everywhere we have characterized that BSR based on those properties, based on those attributes, whatever we defined to characterize the BSR, to identify the BSR. Several other lines. Here also you can see mimicking. The BSR is getting changed as the sea floor is get changed. Here you can see it is simply going like this. BSR also is going like this. It is mimicking. Everywhere it is mimicking. BSR is mimicking. So opposite polarity is very, very important. You can have the opposite polarity. How do you know opposite polarity? If you look into red, black, red, but here you can see the black, red, black, and mimicking. And then it is coinciding with the base of gas hydrate stability. You may observe similar reflector like that, but those reflectors will not fulfill all the criteria what we mentioned. That's why they are not called the BSR. Only one of them, if gas hydrates are present, will be BSR. Okay. And another important thing we told that if hydrates are present, they will be associated with the low attenuation or high velocity. Another 2-3 profiles I am just showing because that was different profile. This is different profile. And here you can see along two lines. This is the BSR. Over the BSR, the seismic quality factor is very high and below is low. High quality factor gas hydrate means low attenuation. And because of the solid substance in nature, hydrate bearing sediments are associated with the low attenuation. Like that, several attributes we can compute for the overlying hydrate bearing sediments and underlying free gas bearing sediments. When I say overlying and underlying, always our reference point is BSR, this BSR. This is associated, hydrate bearing sediment is associated with the low amplitude, associated with the high frequencies, associated with the low sweetness. But underlying gas bearing sediments will be associated with the high sweetness, low frequency, and high amplitude. Already we have seen. Because the frequency absorption into the hydrate bearing sediments will be less. Almost all the frequencies will be there. But the moment seismic wave passes through the gas bearing sediments, high energy, high frequency components will be attenuated. So if we look into the frequency spectra, we'll observe only the low frequency. So there are many ways we can test and we can identify, we can characterize before assessing how much amount of gas and how much amount of free gas are present in a region using the rock physics model. This is one of the important things what I told. That example I showed in the beginning based on one-dimensional full waveform inversion, it shows how velocity varies vertically. Similarly, we can do two-dimensional full waveform inversion by which we will be able to know how velocity varies both horizontally as well as vertically. And once we have that velocity tomogram, and then by using rock physics to the two-dimensional velocity tomogram, we'll be able to know the gas hydrate distribution two-dimensionally and free gas distribution two-dimensionally. If you have 3D volume, then you will be able to know that three-dimensional distribution of the hydrate, three-dimensional distribution of gas in a layer. Based on all these studies, when we are there at, I was there at NGRI, we created a beautiful facility, state-of-the-art gas hydrate research center, where we have been doing that geophysical data processing, modeling, inversion, as well as we also created a laboratory where we have Raman spectroscopy. We are studying what are the characteristics behavior of the methane into a gas chamber, and those based on characteristics visualization, if we have some sort of gas hydrate samples and analyze into the Raman spectroscopy, we'll be able to see by looking into the peak that what are the composition of the gas. So like that we have been pursuing, and we have a very dedicated building. This building is there. If you can visit, we can see that very well established gas hydrate research center. Both we have the data processing centers with state-of-the-art facilities, world-class facilities, as well as we have that facility for the laboratory study. In the laboratory, we create gas hydrate synthetically to understand the formation and dissociation kinetics. Why do that? Because ultimately, towards the production of the gas hydrate, what are the techniques that will help us to produce the gas from the hydrate reservoir in an economic way, in an environmentally safe way? Because I explained that methane, if they dissociate into gas, they will cause a tremendous impact to the environment, not only to the global warming, to the atmosphere, but also to the slope basin. So these are some of the facilities that are available at NGRI. We can do geophysical mapping, modeling, we can validation, coring, geochemical analysis, laboratory analysis, and then we can do some sort of simulation so that we'll be able to know, depending on the geological situation where gas hydrates have been recovered into the KG basin, into the Mahanadi basins, where they are fully clay or they're fracture clay, whether it is a sand reservoir, what type of porosity is there, what type of permeability is there, what are the critical parameters, that means how much saturations we have, how much pore pressure we have. All these things, if we know, we'll be able to understand from the simulation that how and what type of approach we should follow to produce gas from the hydrate reservoir. This is one of the example I am showing, that how the pressure, pore pressure exists into the hydrate bearing sediments. These are the critical parameters that can also be estimated from the seismic data. I told that in a slope basin, if we want to produce gas from the gas hydrate reservoirs, we have to do in a systematic way. Otherwise, if gas hydrates are simply dissociate, this will cause slope failure, debris flow, and a lot of problem will come to the marine environment. So we have to develop the technology such a way we will not vitiate the environment, both in the marine environment as well as in the atmospheric environment, as well as we will be able to produce the gas from the hydrate reservoirs. We had a seminar, international seminar, and we raised some of the questions. And our theme was science and technology of gas hydrates, when they can be produced efficiently and safely. And this was consisting of 2 keynote lectures, 10 national reports, 46 individual talks, 16 oral papers, 6 breakout sessions with distinct titles. So this is some sort of attendee I am showing over here, people from different countries, whatever research they have been doing, they presented in the form of national report, so we can understand what are the status of gas hydrate in their country. So when you look into status of gas hydrate in 10 different countries, we can understand we are sharing thoughts, views, ideas, how we are, because we have to improve our understanding for the, not only for the exploration of the gas hydrate, but also for the exploitation of the gas hydrates. And there are extensive volume is also there. And if you want to know some more, what are the exploration and exploitation status, what are the different technology, what are the different methodology for the exploration, for the exploitation are used, you can find out. There is a one site we have created, and you can find out from there, as well as you can find out some information from this editorial of the Journal of Geological Society of India. Some of the breakout sessions, they raise questions. When will be producing gas hydrates? To answer to that, really it depends on availability of natural gas. At this moment, production of gas from the gas hydrate reservoir will be costly. But in present scenario, now the way prices of oil is increasing, I don't see that barrier for the production of gas from the gas hydrology, gas from the gas hydrate will be there. Because this was the concern when we are talking about that time it was 70, 60 rupees. This is we are talking about long back at the end of 2000, 40 rupees per liter. Now it has cost 100 rupees. So time has come that really we need not bother about that we have to compete with the conventional gas. Conventional gas is also very costly nowadays. So prices, competition is not there. Then unconventional and renewable energy resources, suddenly if there is a breakthrough on the solar or other thing, then we have to bother about that how we'll be able to compete with that. Then geographical location, government's initiatives, lot of things are there. And the type of reservoirs, whether it is a clay reservoir, sand reservoir, etc. So to answer to the question, it depends on many things, but Japan is very, very positive in that direction that they will be producing in full scale by 2028. Another important issue, it was raised that climate change, because most of the constituent gas into the hydrate is the methane, and if methane gets added to the atmosphere, I have already told that will be 25 to 40 times, but that methane has to go through the water column, because these marine gas hydrates, even if they are dissociated, they have to go through the water column and they'll be dissolved, and they'll not get hardly any chance to escape to the atmosphere. So in that breakout session, that was consensus discussion took place that in the climate, that addition of the carbon dioxide, methane from the gas hydrate reservoir will not be that much, but there will be some sort of addition of the methane. They may get that environment polluted into the marine living may get affected. So we have to look into, we should not allow to go out. So we have to devise certain methodology by which we will be able to tap the presence of methane from the reservoir, and that will be produced. Slope instability, already that example I showed, and in the Untitled Chapter, they have seen that as long as slope is less than 10 degrees, there is no problem, or there is no slope failure, there is no mass failure into that region. So as a whole, in the concluding remark, and before going to the concluding remark, I'd like to place before you, since we have told that gas hydrate is stable at high pressure and low temperature. So how we'll be able to produce? There are different methods people are thinking of. Simple thinking is that since they are stable at high pressure and low temperature, why don't do the depressurization of the gas hydrate reservoir? Why don't heat the that gas hydrate reservoir, so that by heating, the gas hydrate will be dissociated into the gas, and that gas can be pumped out. by depressurization of the gas hydrate reservoir, the gas hydrate will be dissociated into the gas, and that gas can be produced. Gas hydrates cannot be stable in presence of certain, just like methanol, etc., inhibitor. So if we inject methanol like inhibitor, then gas hydrate will be dissociated into the gas, and that gas can be pumped out. Or a combination of all these, whatever I showed into the second slide, that test production by Japan, China, Canada, they have done, and Russia, India, and America, they are done based on all these depressurization method, or a thermal injection, or maybe chemical injection, that inhibitor injection, or a combination of both. Nowadays, research is going on carbon dioxide sequestration. Carbon dioxide, all of us know that we need to reduce that carbon footprint. And one of the best effort is going on how we can sequester the carbon dioxide. If we inject the carbon dioxide into the methane hydrate reservoir, carbon dioxide hydrate is more stable than methane hydrate. So what will happen? There will be chemical replacement. That methane will be replaced and carbon dioxide will sit in its place. So by the molecular substitution and doing this carbon dioxide sequestration, we can get two-fold of benefits. One is that we'll be able to reduce the carbon footprint. Other one will be able to produce the methane from the methane hydrate reserve. We have seen a lot of gas hydrates, and the gas hydrates have been recovered. Whatever we have done from the surface experiment, one of the example I am showing over here in the KG basin, that wherever locations we have given for the BSR, by drilling, coring from their gas hydrates have been recovered, and that shows the validation of the seismic experiment for the identification of the gas hydrate, for the characterization of the gas hydrate. Now we look forward, just like 4 countries, in our country also, at least one site into the KG basin we should do for the test production. Then it will show and demonstrate that in our country we are able to map the presence of the gas hydrate, evaluate the potential of the gas hydrate, as well as we are also able to test produce gas from the gas hydrate reservoir. And whenever there will be a foolproof technology available in the world, we will be able to produce gas from the gas hydrate reservoir from the along the continental margin of India to meet our overwhelming energy requirements. So thank you very much, and it's a great pleasure for giving this webinar. After a long time, I am talking on the gas hydrates. I have been doing something different nowadays at WIHG to the Himalayan geology. Thank you very much.
Thank you so much, sir, for your informative talk. I'm sure your ideas will inspire all of us to act towards the protection of environment by utilizing alternative energy resources and so on. Sir, President, sir, would you like to say something?
Yeah, no, I would like to thank and congratulate Dr. Kalachand for giving a wonderful overview of the gas hydrate exploration, the kind of techniques which are being used, especially all the fundamentals and theories, for the gas hydrate formation, and then how the seismic techniques are being used, and his work, and along with his co-researchers, how they have now tried to do entire mapping, especially in the Indian context, and the potential which is available today. This is a very significant amount of work which has come out from this research. And today, sir, we are so thankful that you have provided a very wonderful overview to all our members about this upcoming area. Definitely, I think in future to come, as you have suggested, the exploration activity, especially the commercial exploitation of some of these gas hydrates, considering the petroleum prices and the energy crisis world is facing, I think some more emphasis will happen. So definitely, I think it is a technology, probably maybe in times to come, this will be exploited. And as you have suggested that there is enough potential in our EEZ region that can be very helpful for us for next 6 to 7 decades. So definitely, I think as we go along, more and more refined technology for the exploration and exploitation of these resources will emerge. And on my personal behalf, as well as on behalf of ISRS, members, I would like to thank and congratulate you on this wonderful talk, sir. Thank you very much.
Thank you very much, Dr. Prakash.
Dr. Poonam? Her connection, it seems, is lost. Maybe there will be a formal vote of thanks to you.
Thank you, sir. And before closing today's program, I would like to thank Dr. Prakash Chauhan, President ISRS, for his support and encouragement towards organizing this event. Thanks are due to Dr. Kalachand Sain, Director, Wadia Institute of Himalayan Geology, for taking time out from his busy schedule and delivering this talk, very informative talk for all our members. Thanks are also due to all EC members for their support towards organizing this program. My heartfelt thanks are due to Dr. Praveen Thakur, Secretary ISRS, who has planned this entire event very meticulously. I wish to thank all staff and ISRS headquarters for their efforts in organizing the event. And lastly, I would like to thank all the members of ISRS and the audience who have attended this session and made this session a grand success. Thank you all. Thank you, sir.
Thank you, sir. Thank you. The session will be available on a YouTube link also, sir, for later on. Maybe you can send the link to sir. Thank you, sir.
Thanks. I'm leaving.